Hi there, so we're going to be continuing with Chapter 8, Potential Energy and Conservation of Energy. In this chapter, we're going to be defining conservative forces and potential energy, and then you should have some sense of or know what the principle of conservation of mechanical energy refers to. Then we're going to go on to derive the potential energy associated with gravity. Determine the work done by non-conservative forces. So we're going to be looking at non-conservative forces and working with them, and derive an equation for the potential energy stored in a spring. And this is very much building on what we did previously in terms of we started looking at springs and Hooke's law. And then, of course, most importantly, we should be able to solve problems relating to all these individual concepts. In this chapter, we're going to be using a different approach to the previous approach to solve problems. In the previous chapters, we considered objects that were subject to external forces. For example, we would look at a book that's subject to gravity or an applied force. Now, in this new chapter, we're going to consider systems as a whole, subject to internal forces and the changes of the internal forces. So this is to say, if we have the case of this book being acted on by gravity, then we're going to consider the system of the book and the earth interacting as a whole system. So in this example, we're going to be looking at the work done by external applied force to lift the book. And this results in the potential energy that's stored in the book, increasing. So here we have a force being applied, and this force is lifting a book. So the work done by the force, by the external force, can be expressed as following. We have the work done by the external force, that's what EXT means, is equal to the applied force dotted with the displacement vector. Remember, this is from the definition of work. Now, if we look at what each of the individual terms are, we see the applied force will need to be mass times gravity in the positive j hat direction, because the force is being applied upwards to lift the book upwards. And the displacement is also going to be from this point here upwards. The distance that the book is going to move is going to be YF minus YR, and the displacement is also going to be in the positive j hat direction because the book is being lifted upwards. If we take note that when we take the dot product of the individual vectors, j hat dot j hat is just going to be 1. And then using the distributive law of multiplying mgn, we get the work applied by this external force is given by this expression here. It's interesting for us to look at the form of the terms just derived, and you'll note that each of the terms are in the same form. And then from this, we go on to define the gravitational potential energy of an object with mass m, as the gravitational potential is defined as mgy, where y is the height of the object relative to the ground or the reference frame. The gravitational potential energy, it has units of joules, and in fact this is the same units of work and kinetic energy which we've already seen, which also have units of joules. For our example with the book, the work done by the external force equals the change in the gravitational potential as expressed in this formula here. So next, we're going to be looking at what happens when we have a frictionless surface and we have a person, they're pushing a block of mass m and they're pushing it against a spring, and the spring is becoming compressed, and they push it to a position of maximum compression of the spring, denoted by x max, and then they let the spring go. And for us, we're interested in looking at what happens to the block or the whole energy of the whole system in terms of three things: the kinetic energy stored in the block, the elastic potential energy stored in the spring, and then of course the total energy. So to start off with, initially we have no energy in the system, and then as the person pushes the block against the spring, we have elastic potential energy being stored in the spring. And as the block is being pushed, the elastic potential energy is increasing. So we see this bar increasing. And of course the total energy is just the amount of elastic potential energy in the system. As the block is pressed further against the spring, it comes to X max, the point of maximum compression of the spring, and there we've seen the potential energy of the system increase, and of course the total energy has also increased. If we go on to look what happens after the block is released, so after the block is released, initially the spring will still be in contact with the block, but of course the block will start moving with some velocity v. And once the block starts moving, we can see then kinetic energy has been introduced into the system. And of course the potential energy has now decreased. So the potential energy has decreased slightly from this point until being much less than before. And the reason for this is that the elastic potential energy stored in the spring has now decreased. Of course, the elastic potential energy stored in the spring, it isn't zero yet, because the spring isn't at its equilibrium position. The total energy then can be obtained by summing these by summing the kinetic energy and the potential energy together. What will eventually happen is the spring will reach its equilibrium position, and at that point the block will go on its way with some velocity that will then remain constant. And in terms of our little chart representation of what's happening with the energy, we can see that here the kinetic energy will be at its maximum, and there's no longer any potential energy stored in the system. The reason for this is now because the spring is at its equilibrium position, and then the total energy will just be equal to the kinetic energy. So this is an interesting example. It's interesting in the sense that it forces us to think about what's happening in a different way. We're not only focusing our attention on the object, on the block, but now we're interested in looking at the whole system, where the system is the block and the spring. And also we're interested in looking at it from an energy point of view. We're interested in what's happening to the kinetic energy of the block as it's moving, and we're also interested in what's happening to the elastic potential energy stored in the spring. And at the same time we're interested in the total energy of the whole system. So next we're going to be looking at conservative forces and non-conservative forces. There are two different ways which we can define or state what a conservative force is. The first way is conservative force. It has the properties such that the work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. When we speak of conservative forces, examples are the force of gravity or the force of a spring. So if we look at the interpretation of this first point in the context of a book being acted upon by gravity, what we have is a book starting at position A, and we want to lift it to point E, the top of this cupboard. So there are many different ways in which we could do it. The first way is we could lift the book directly along this path shown in the green line from point A to point E. That would be one option to get it to the top. A second option is that we could take it on a lot longer path. So we could start at point A and then move it up to point B, then move it all the way up to here, stop at point C, go all the way around, even higher than the bookshelf, and then finally bring it to the top. So it could move to point E through point A, B, C, and D. And what since gravity is a conservative force, it means that the work done by gravity will be the same in each of these two cases. It will be independent of whether you take it on this long route or if you take it on a short direct route. The work done by gravity will be the same in both cases. And the reason for this is gravity is a conservative force. And in fact, from school, you already have been familiar with how you would calculate that work done. You would just use mgh, where h is the height of the bookcase, right? You wouldn't worry about the path. An equivalent property of conservative forces is that stated by point 2. The work done by a conservative force on a particle moving through any closed path is 0. And a closed path is a path for which the beginning and the end points are identical. The second property is actually a consequence of the first property, and I'd like you to think a little bit about that yourself. But you can imagine the book being moved from point A to point E directly along the short path, and then being returned through point D, C, B, and A, such that it returns to its starting position. In this sense, the book has moved through a closed path because its beginning point is the same as its end point. And we note that the net work done on the book is actually 0. The reason for it being 0 is that we haven't changed the kinetic energy of the book. It was at rest before we started, it's at rest at the end. It's in exactly the same position, so its potential energy is exactly the same, before we moved it compared to once it returned. A non-conservative force is a force that does not satisfy either of these two properties which we've just seen. For a non-conservative force, the work done by the non-conservative force, it is path dependent. So the amount of work done by a non-conservative force, it depends on the path. Examples of non-conservative forces are friction and also air resistance. In this example shown here, we have a book on a table, and in this case there is friction present on the table, between the table and the book. And you can consider moving the book along two different paths. The first path is a long path shown by this brown line. The second path is a shorter, more direct path shown by the blue line. And in fact, because of friction, because of the non-conservative force, the work done in moving the book is greater along the brown path than along the blue path. So this then wraps up the concept of non-conservative forces. Another important concept is that of mechanical energy, and we define the mechanical energy of a system as the sum of the kinetic energy plus the potential energy of that system. Right, so next we're going to go on and apply the different energy concepts we've seen to the conservation of mechanical energy. Before we do so, I think it's important for us to remind ourselves of all the different types of energy that we've seen up until now and the symbols that we're using. So remember, we've seen we have work can be done, and we express that by capital W. We have potential energy, and the symbol we use for that is a capital U. In terms of potential energy, we've seen gravitational potential energy with a book being lifted against gravity, and we've also seen elastic potential energy with the energy stored in a spring. And we also have kinetic energy, which we defined as half mv squared, and we expressing that with a capital K. We have then also the work energy theorem, and the work energy theorem said when work is done on a system and the only change is in the speed of an object, then the amount of work done is its change in its kinetic energy. So therefore we express that as the work is the change in the kinetic energy. And from the previous slide, we've just seen when speaking about a system, we would like to consider the kinetic energy plus the potential energy, and that we call that the mechanical energy. And the symbol that we use for that is a capital E. So if you become a little bit confused and want to refer back to what all the symbols mean, this is a good slide just to remind yourself of that. So in this section, we would like to look at the conservation of mechanical energy. And specifically, we would like to look at what happens when we have conservative forces acting. And what we would like to do is we would like to show that mechanical energy is conserved when we have conservative forces acting. It's important for us just to remind ourselves exactly what mechanical energy is. Remember, mechanical energy is the sum of the kinetic energy plus the potential energy as shown here. So then, the situation we're looking at is we're looking at the case where we have a book which is initially at rest, and then the book is dropped, and as the book is dropped, it falls through some distance, and as it approaches the ground, it will be speeding up, its kinetic energy will be increasing. So what we would like to do is, like we consider in this is the initial case with the book up here, and this is the final case, and what we would like to do is show that the mechanical energy is conserved we would like to show that mathematically. So we know then from the work energy theorem, the work done is the change in the kinetic energy. That's the one expression we know. Secondly, we know the work done on the book will be the change in its potential energy. Here we have a negative sign included, and the reason for that is as the book falls, its potential energy will decrease. So we can combine these two equations, and then we get delta K is equal to minus delta U. Just rearranging, we get delta K is equal to plus delta U is equal to 0. Now we need to remember that whenever we have a delta, it's referring to a change. So if we have change in kinetic energy, we can rewrite that as the change in the final kinetic energy minus the initial. And we do that similarly for the potential energy. We write that as a final minus initial. In the next step, we group the terms relating to final and the terms relating to initial. Here we can see within this bracket, it's the final kinetic energy plus the final potential energy. But remember, kinetic energy plus potential energy, by definition, that's mechanical energy. So this means that going from this step to this step, we can replace this final kinetic energy plus final potential energy with the final mechanical energy. And similarly, this term here, these two terms in brackets, can be replaced with initial mechanical energy. And then finally, we can end up with the result that the final mechanical energy is equal to the initial mechanical energy. And this thing goes on to show what we were trying to show, that the mechanical energy is conserved for conservative forces. So we go now to solve a problem using conservation of mechanical energy. And the problem states that the center of mass of a pole vaulter is 1 meter above the ground. If he can run at 10 meters per second, how high can he vault, or how high can he jump. So here I've summarized the the information that we have in a little diagram. You can see we have the pole vaulter. They refer to center of mass as being 1 meter above the ground. Remember, we use the concept of center of mass when we have a complicated shaped object, such as a person with arms and legs and a pole. We're just saying that we condensing this person down into a point mass and treating them as a point. So initially, we have the case of this pole vaulter as shown, and the center of mass is 1 meter above the ground. So that's the initial height, HI. And then they say initially the pole vaulter is running at 10 meters per second. And then what's going to happen is they're going to, perform their pole vaulting maneuver, and they'll end up at the top of the they'll end up in the sky. So when we look at that, then you need to realize that their velocity at the point will be 0, right? And when we ask to calculate how high can they vault, how high can they jump, then we ask to calculate what is their final height. So as I said, we'll be using the conservation of mechanical energy to solve this problem. And essentially the conservation of mechanical energy tells us that the final mechanical energy is going to be equal to the initial mechanical energy. So what we do then is we go ahead and expand the terms and write out the equations. So the final mechanical energy, referring to this case, remember mechanical energy is the sum of the kinetic energy and the potential energy. This is going to be equal to the initial mechanical energy. So we expand for the initial kinetic energy plus the initial potential energy. You'll see that throughout this line we have the mass of the pole vaulter appearing everywhere, and for that reason we can cancel out the mass. And then what we can do is we can simply rearrange for the final height. Remember, that's what we were trying to find, and this turns out to be given by this expression here. We in fact know all the terms. We know what g is, we know what the initial velocity, this is this 10 meters per second. The final velocity is going to be 0 because now the person is suspended for that moment in air at the top of their trajectory, and the initial height is 1 meter. Substituting the values in, then we come out to an answer of 6.1 meters. A few slides ago we saw that mechanical energy is conserved for conservative forces. Now we would like to check if that's the same for non-conservative forces. So non-conservative forces, they are present in real life. You remember the examples we used were air friction, or air resistance and friction. So now if we consider the total work done in the case where both non-conservative and conservative forces are acting. So for example, this might be the case of someone jumping out an aeroplane, and there is air friction acting on them, which is a non-conservative force, but there's also gravity acting on them, which is a conservative force. So in such a case, the total work done will be the work done by the conservative force plus the work done by the non-conservative force. It's equation 1. We can then apply the work energy theorem to get equation 2. As before, the work done by the conservative force will be the change in the potential energy. Substituting 2 and 3 into 1, we see the change in the kinetic energy is minus the change in the potential energy plus the work done by the non-conservative force. So then we have the work done by the non-conservative force is the change in the potential energy plus the change in the kinetic energy. We go through the same steps where we unpack the notation and we rewrite the delta in terms of the final minus the initial. We do that for both of the terms, just as we did before. Again, we group the two final terms and the two initial terms, and we remember that the kinetic energy plus the potential energy in each case is the mechanical energy. And here we get, finally, the work done by the non-conservative force is the final mechanical energy minus the initial mechanical energy. So the work done by the non-conservative forces is the change in the mechanical energy. In this case, we can see that the difference isn't zero. It's actually the work done by the non-conservative forces. So here we've shown that for non-conservative forces, the change in mechanical energy isn't zero. So energy is in fact lost to the system, and it's lost through mechanisms such as friction or sound or heat being produced. And this leads us to the important conclusion that mechanical energy is not conserved for non-conservative forces. Of course, we have the total energy being conserved. Thus, we need to obey the laws of nature, and they state that the total energy will always be conserved. So we aren't violating that fundamental principle. So now we're going to solve a problem which involves both a conservative force, gravity, as well as a non-conservative force, friction. The problem states a block of mass 4.5 kgs is projected up an incline of 30 degrees with an initial velocity of 5 meters per second. The block moves 1.5 meters up the slope, stops and slides back down to the bottom of the hill. And then we asked to perform a number of tasks or solve a number of problems related to this question. So first, it's important for us to understand what the question's asking. So I've made a sketch of the situation. They're referring to a block of mass m, 4.5 kgs. It's projected up a slope, an incline of 30 degrees with an initial velocity of u equals 5 meters per second. It moves up the slope. At the top it will stop, right? And the reason why it will stop is because gravity's sort of acting downwards, pulling it downwards. But we also have friction in the system. So what happens is on the way up, friction will be removing energy from the block. And then on the way down, or once it's stopped, it will then slide back down the hill and it will reach the bottom again. But due to the force of friction, the speed that it reaches at the bottom, it isn't going to be the same as this 5 meters per second, because the non-conservative force friction has removed energy out the system. So we expect the velocity at the bottom to be less than 5 meters per second. And we asked to in fact calculate this velocity, and we also asked to calculate the friction force. And we given the angle is 30 degrees, we given the length of the slope is 1.5 meters. From that, we're able to use the geometry of the situation to calculate the height. So the height of the slope, we can simply calculate that using sine. And if we also needed to, we could calculate the length along the bottom using a similar cos relation. Let's take a look at the first part of the question as well as the solution thereof. So the first part asks us to draw the forces acting on the block as it moves up the slope. Show also the appropriate choice of axes for solving this problem. So over here I've already produced the solution. The appropriate choice of axes for an object on a slope is, that choice which corresponds to the orientation of the slope as shown here. When it comes to drawing the individual forces, the first force to note is the force of gravity, which of course acts directly downwards as indicated. We're going to have the block being in contact with the surface. So that means that there's going to be a normal force, and the normal force is going to be perpendicular to the surface. Just returning briefly to the force of gravity, of course we could also break that into its components. The third force that we're going to have acting is the force of friction. This is in fact going to be kinetic friction. The block is going to be moving up the slope, and for that reason the friction is going to be operating in the opposite direction. It's not asked for in the question, but I've taken the liberty of defining each of the forces as well as writing some of the equations out. So for the force of friction, it's going to be the coefficient of friction times the normal force. And remember, this is going to be operating in the negative r-hat direction. The force of gravity is just going to be mg. And as I previously mentioned, we can break the force of gravity down into its individual components. And these components would be an x component pointing in the negative r-hat, and a y component pointing in the negative j-hat. When we're dealing with the slope, an example of this case, remember that the x component, it follows sine of theta, and the y component follows cos of theta. This is different to the normal convention. The reason for this, as we've dealt with previously, is that we're dealing with an object on a slope. The second part of the question asks us to calculate the acceleration of the block as it moves up the slope. So remember, what's happening is the block is moving up the slope. It's moving a distance of 1.5 meters up the slope, and then it's coming to rest and stopping. So this means that it has an associated acceleration with its motion, and we asked to calculate that acceleration. So from the information given, we given a number of quantities. We know that the initial velocity is 5 meters per second. Note that taking care of the signs here is important. It's moving up the slope, and up the slope was defined as the positive x direction. We're interested in the point at which it comes to a rest at top of the slope. So its final velocity would be 0. And it comes to rest after a distance of 1.5 meters per second. And given this information, we see that we can use this equation, v squared is equal to u squared plus 2as. Since we know v, we know u, we know the distance is 1.5 meters, and then we can rearrange that to find out what the acceleration is. It comes out to be that the acceleration is negative 8.3 meters per second squared. Of course, the reason that the acceleration is negative is that as the block moves up the slope, it's in fact slowing down to come to a rest. The next thing we asked is to find the force of friction acting on the block. So the way we solve this problem is we apply Newton's second law in the x direction. So working in the x direction, then we have the sum of the forces is mass times acceleration. Remember, we've already found the acceleration in the x direction here. Applying the forces, we're going to have the force of friction, which is acting down the slope. This then is the x component of gravity, which is acting down the slope, is equal to mass times acceleration. We can then rearrange the terms, and we find that the force of friction is given by this expression here. We know what the mass of the block is, right? We're given that that's 4.5 kgs. The acceleration x, we've already found out what that is. That's that value there. We know m and g is fine, and we're given the angle being 30 degrees. And calculating this, it comes out to be that the force of the kinetic friction is 5.5 newtons. It's not asked in this problem, but it could have been that you were asked to calculate what is the coefficient of kinetic friction, mu k. Well, if you were asked that, you could have gone on to use this result for the force of the kinetic friction and use the expression the force of kinetic friction is equal to mu k times the normal force. From your force diagram, you would have been able to find out what the normal force is, and then from that you would have known what the normal force is, and here we just found out what the force of kinetic friction is, and that would have then allowed you to solve for mu k, the coefficient of kinetic friction. For number 4, we are asked to calculate the work done by friction on the block as it moves back down the hill. So in this case, we're going to make use of the definition of our definition of work, and of course our definition of work is the dot product between force and displacement. So it's the force of kinetic friction in this case, the displacement distance, and cos of theta. If we go on to substitute the values in, we previously found that the force of kinetic friction was 15.5 newtons. The displacement is going to be 1.5 meters. The reason for that is that our block is moving 1.5 meters up the hill to the top. The third term we need to substitute in is for cos of theta. Here you need to be a little bit careful. We don't use this theta as 30 degrees, the slope of the hill. We need to remember, we need to use the angle between the force of friction and the displacement. So for us, the force of friction is acting down the hill, and the displacement is up the hill in this direction. So the angle is going to be 180 degrees because the friction and the displacement vector are in opposite directions. And the solution then comes out to be that the work done by friction is minus 23.25. The minus is an indication that energy is being taken out the system by the non-conservative force of friction. We are now asked to find the velocity of the block upon its return to the bottom of the slope. So we consider in the case where the block has now reached the top of the slope, it stopped, and it's going to now be moving from rest down the slope to the bottom of the slope. Well, we know initially the block was, projected up the slope with a speed of 5 meters per second, but because we have friction acting, it's going to be removing energy from the block as it moves up and down the slope. So for that reason, we expect the speed upon its return to the bottom to be less than 5 meters per second. And the way we solve this problem is by making use of this equation here, where the work done by friction, the non-conservative force, as the block moves down the slope, will be given as the difference in the mechanical energy. Again, we expand the terms for the mechanical energy in each case. Mechanical energy is kinetic energy plus potential energy. We do that for both the final and the initial energies. We've already found the work done by friction as the block moves down the slope is this value here. We know that the final height, for the final height HF, the block is going to end at the bottom of the slope, so we can make this 0. For the initial velocity, the block is moving from the top of the slope, where it has an initial velocity of 0. Remember, it stopped there, so this term here is going to fall away because u is 0, and we're left with that term. And then simply we can rearrange this expression and make a Vf the subject of the equation. And in this case, we know all these quantities, we know M, we know G. So we're able simply to compute what the final answer should be. We take the square root of 4.367, and we find that to be 2.09 meters per second. In this case, remember, we take the negative square root because we have the block will be moving down the slope in the negative I-hat direction. So that's the reason why we've used the negative value. And it's satisfying for us to see that this 2.09 meters per second, that's less than the 5 meters per second initial velocity of the block due to friction, which is what we were expecting. We now conclude this chapter by looking at the potential energy stored in a spring. Well, previously, once we had learned to integrate, we saw that to elongate a spring requires some amount of work given by half kx squared. So this work then can be equated to the potential of the spring. Equating these two terms, we get the change in potential is equal, change in potential energy is half kx squared. If we consider the case where the spring initially had a potential energy of 0 and it was initially at its equilibrium position with xi equals to 0, then we just see that the potential energy stored in the spring will be half kx squared. So this gives us then an expression for knowing how much potential energy is stored in a spring as a function of its position x, or as a function of its elongation factor x. And we can go on to look at the total mechanical energy stored in the spring system, and this will consist of any kinetic energy that's present, any potential due to gravity, and of course then the potential energy stored in any elongated or compressed springs within the system. By means of an example, we can look at this figure shown here. Here you can see we have a number of two different mass pieces, and we have potential energy stored in this mass piece, right, by virtue of gravity. This spring may be compressed relative to its equilibrium position, so there'll be some potential energy stored in this spring system. It could be that after some time this mass piece will start moving, then we will have kinetic energy in the system. Kinetic energy resulting from both mass piece 1 and mass piece 2 as the blocks move down. This then concludes chapter 8 and our work on potential energy and the conservation of energy.